All right, guys, let's continue with our talk about global climate. Remember, we talked last time about several different things that affect overall global climate. We're going to pick up here with number 3. So number 3 is the Coriolis effect. Basically, the Coriolis effect is that the Earth rotates, and since the Earth is constantly rotating, that the Coriolis effect basically means that things are going to get, their path is going to get deflected because of this rotation. You can kind of think of it as the object wants to move in one way, and yet the Earth is moving underneath it. Okay, and so let's look at essentially what that means for us here. These two diagrams over here are essentially showing the idea of the Coriolis effect. And so the idea would be if you threw a ball, say from the North Pole, okay, that ball is going to travel in a straight line path. Okay, that's what the laws of physics say, right? Until there's something there that's able to actually slow it down. So if I took something and I threw it for, if I took something and was at the North Pole here, okay, and so I then threw that, it should travel in a straight line path, except that I obviously can't draw a straight line. But that should travel in a straight line path. Now, what actually happens, though, of course, is that all the time that this is happening, the Earth is moving underneath this, okay? So the Earth is spinning. So while it's traveling in a straight line right here, so if we drew our nice little line here, and really color pink not working for us there, we draw a straight line path there, it is traveling in a straight line. However, the Earth is moving under it. And so that makes it appear, okay, or makes that object seem as though it has a curved path. So instead of ending up, if I threw a straight line here, instead of it ending up in, say, Maine, that it ends up somewhere way out here, okay? So that's an example of the Coriolis effect. That spin is going to alter basically where everything is going to go. And see, this is a good example of this. It's as though the ball is traveling in this curved line path. Now, in reality, it's not, okay? The Earth is spinning underneath it, but this is going to have some pretty big effects for us, particularly to do with wind, and that's where we're really going to talk about it for. So if you remember, when we had the video on the other stuff, we were talking about Hadley cells, and if you recall, a Hadley cell is we've got an intertropical convergence zone, okay, somewhere around here. Remember that we've got an equator down here around this area, and remember the ICTZ changes places. Sometimes it's north of the equator, sometimes it's south, okay? But we've got this intertropical convergence zone, and then we have Hadley cells, right? Okay, and so what's going on in the Hadley cell? Okay, tropical area, heating up, okay? Air is going to get heated up, some of it's going to condense, and some of it's going to condense. That's going to warm it up, and eventually it's going to keep heating up. Eventually, as it gets up higher and higher up, it's not going to keep heating up, sorry, it's going to keep rising. It's going to keep rising, and eventually, as it rises, it's going to cool down, and then it's going to come down and loop back around, right? And so that drier air now is going to come back down. So very moist air gets heated up in the tropics, it goes up, then it's going to lose its moisture. It's going to cool down. It's going to come back down as very dry air, and that air is going to then circulate back to the tropics. And so, if you remember, what we said is that if the starting point here of it heating up starts at the ICTZ here, okay, then that's going to rise up, right? I'm sorry, ITCZ. It's driving me crazy. So it should rise up, and then it's going to rises up, and then it's going to come back around this area. And so theoretically, that should be kind of a straight line sort of thing, right? Okay, so it's going to rise up. So it's going to rise up here at the ITCZ, and then it's going to go up in the atmosphere, and then it's going to come back down somewhere around 30 degrees latitude or so, and then start to come back to the tropics, okay? And that should happen in pretty straight line patterns, really, except that the Coriolis effect is there, right? And so the Earth is constantly rotating, and the fact that the Earth is constantly rotating is going to cause those wind patterns to shift. And so this is basically the result. So remember we had these cells. We had Hadley cells, we had mid-latitude cells, we had polar cells, and then the fact that the Earth is rotating is going to cause all of these changes. So the Hadley cells are then going to result that the wind as it comes back at the bottom of the Hadley cells there, the air as it comes back at the end of the Hadley cells, if there were no Coriolis effect, then essentially it should come back in these nice little straight lines, okay? But that's actually not what happens. What actually happens is that it's curved, okay? And it's curved because of the Coriolis effect. Okay, and that's going to result in these very distinct wind patterns that we're going to have here. Okay, so what sort of distinct wind patterns do we have? Well, let me erase all this junk real quick. And so our distinct wind patterns are we've got these trade winds that are in the Hadley cell zones that are in about between 0 and 30 degrees each way. So winds basically blow from the northeast and from the southeast in each of those zones. And then in the mid-latitude cells, we've got what we call westerlies, that they're basically blowing from the west. It's important to note that when we're talking about wind directions, that essentially what we're talking about is where they're coming from, not where they're blowing to. So if we say that we've got a northeaster, then that means it's blowing out of the northeast. If we say we've got westerly winds, they're blowing from the west. Okay, so you see we've got these westerlies in the mid-latitudes, okay, there and there, and those are, again, largely due to the Coriolis effect. Okay, winds, even if the air was moving stable, the Earth is rotating counterclockwise around that, and that's going to cause the winds then to blow these directions in these areas. Trade winds, okay, and then polar regions. Well, what do we have going on in polar regions? Well, basically they're blowing from the poles, okay, in southerly directions, or if we're talking about from the South Pole, in a northerly direction, basically away from the poles. Okay, so those are major areas of wind flow. Okay, so let's talk about reason 4 real quick, and then we'll jump to reason 5, which is the biggest one. So we've already said that the fact that the Earth is tilted results in uneven heating. And so again, we want to just sort of reiterate that point that the Earth's tilt and seasons are going to result in that uneven heating that's going to say, hey, in this time of the year, we're going to have a lot more heat. At this time, we're going to have a lot less heat. A few terms to go along with that I think you guys should know. Equinox, basically an equinox is when the sun is directly over the equator. And so most of the Earth on that day gets about 12 hours of daylight and about 12 hours of darkness. So we've got 2 equinoxes a year. Okay, so the equinoxes happen in the spring and autumn. So we've got a spring and an autumnal equinox. And so that would be at around March 21st, okay? And around September 21st, when we have our equinoxes. And then we have 2 things called solstices. And the solstices basically are either the longest or shortest day of the year. And of course, it depends on which hemisphere you're in. So in June, we've got the summer solstice, which is the longest day of the year for us in the northern hemisphere, shortest day in the southern hemisphere. And then in December, we've got the winter solstice, which is the maximum tilt away from the sun. And so therefore, we're going to get the shortest day of the year. So in June, the summer solstice, okay, maximum facing towards the sun. December, least amount of facing towards the sun for the northern hemisphere. Okay, so just make sure you know those terms. Of course, that's going to have some big effects on weather. I mean, obviously, if we're towards the winter solstice and we're getting less sun, then things are overall going to be colder. If we're in the summer solstice and we're getting more sun every day, solstice, then we're obviously going to be warmer. All right, so one of the biggest driving effects of weather, obviously the sun is the overall driver of everything. Just like we said for trophic levels, most energy comes from the sun. Most of our weather effects ultimately derive from the sun. But another big player in this are ocean currents. And ocean currents, the reason that ocean currents are so important is because water has a really high specific heat. Water can absorb a massive amount of heat, and therefore there's a lot of energy stored up in water. And since our planet is mostly water, then that means there's a lot of energy stored up in those ocean currents. So those are going to be affected by all kinds of things. They're going to be affected by temperature, gravity, winds, the Coriolis effect, and where the continents are. All of these things are going to affect where do the ocean's currents flow. Okay, so a couple of terms for us. Basically, there are 5 giant scale patterns in the oceans, and these are what we call gyres. Gyres are large patterns of water circulation, and they're pretty easy to see. There are 5 of them, 5 main gyres at least, and they correspond to each giant basin of water. So there's one in the North Atlantic here and the South Atlantic. There's one in the Indian Ocean Basin. There's one in the North Pacific, and there's one in the South Pacific. Those are the 5 main gyres there. Another thing that's kind of important for us is that we get these upwelling patterns. Upwelling basically means that the cold water usually sits on the bottom, right? Okay, because cold water is denser than hot water. So hot water on the top, cold water on the bottom. But in certain areas, we get what we call upwelling, where the cold water sort of moves up to the surface. And so there's a big one here sort of on the coast of Peru. There's another one here around Baja California or so. There's one over here in Africa. There's definitely one over here in Australia. So generally on the western coasts of the continents, we're going to get a little bit of upwelling of cold water. Now that's really important because what the upwelling does is that it brings up a lot of nutrients to the surface. Where there's a lot of nutrients brought up, the phytoplankton got a lot of nutrients to feed on and produce energy. Those phytoplankton, of course, are consumers. They're going to get consumed by zooplankton and then by all kinds of other things. So it tends to be in these areas where you get a lot of upwelling. You've got a large, massive reserve of good fishing and of wildlife and stuff like that. So gyres, large-scale circular patterns. The other big thing for ocean currents is the thermohaline circulation. So we can break that word down. Thermo, okay, I don't think that's a big mystery to any of us. Thermo means heat, okay. Haline might be a little bit different, but haline basically means salt, okay. That comes from halides. So halides, sodium chloride. Chloride is a halide, and so that's where that's going to come from. So the thermohaline circulation is basically the fact that the more salt that's dissolved in the water, that has a great effect on where these overall currents go. And so basically the way that we can look at that is, what I want you to look at on this map here is that there are a couple of places of what we call deep water formation. And what that means is that this is where there's really high salinity and really cold water, and so therefore that's going to sink down to the bottom. So you see this flow here of this cold water flowing. You also see this sort of continuous flow of cold water near Antarctica. And so those are flowing basically under the surface. Okay, these are deep currents. And then we've got surface currents on the top where it's much hotter and generally speaking, much less salinity. So we're going to talk later this year when we talk about water resources, but this is really important because what happens as, say, the polar ice caps melt and we get a lot more fresh water, that fresh water dilutes the salinity, and the lower the salinity then, the more able that stuff is to rise up, and so then we wouldn't get this circulatory pattern going on, because instead of the warm water going up and then cooling off in the Arctic and getting more salinity and sinking back down and then being able to circulate, if this stops here in these polar regions because of melting ice caps, then we're not going to have the same ocean patterns. And if we don't have the same ocean patterns, then we're not going to have the same weather patterns, and that's going to affect things pretty drastically. The other big thing here is heat transport. So we said that the ocean or water in general is a big sink of heat, that it holds a lot of heat in, and so it transports a lot of heat around the globe. To me, always the biggest example of this is right here. If you look at Great Britain, okay, these are the British Isles right here. Draw yourself a line across the map to the rest of the world that's at that latitude. So if you draw that around, okay, think about the area that is roughly equivalent to that around the rest of the world. So where are we talking about? We're talking about like almost Alaska. We're talking about like Canada, Siberia, some extremely, exceedingly cold places. And yet Britain, really not that terribly cold. It's cold. I mean, it definitely has some cold areas, but really, if we look at this, I mean, like, just look at, say, let's look at Italy. In Italy, in the Mediterranean, we think of it as like these sort of nice, almost not quite tropical, but these nice sort of warm areas. But look where Italy would be equivalent to in the United States. It would be like New England, Maine area. Okay? Obviously, a massive difference here. So what's the difference? I mean, why is Europe kind of, a sort of very temperate sort of place where if it was, say, in North America or in Asia, it would be really cold? So why is that? Well, that's basically because of the heat transport of the ocean, because really what's going on is we've got warm water coming out of the Gulf of Mexico, and it forms this very warm current of water that basically sort of flows up past Britain towards Europe. And that massive amount of heat in the ocean there is essentially going to keep those areas warm and much more temperate than they would be otherwise. Another reason why Europe in particular should be really worried about global warming and the melting of the ice caps, because if the ocean currents change, then chances are their climate is probably going to alter to be somewhat similar to the rest of the things at their latitude, which would be pretty dangerous for them. The last thing here that we want to talk about as far as ocean currents is the condition known as El Nino. So El Nino occurs in the Pacific here. So in the Pacific, this is the normal function of the Pacific, is that we've got warm currents going this way, and we've got an upwelling of cold water going on here. There's a nice little pattern here. Now, why that matters so much is that what that leads to is it's sort of a normal convective loop above it of the atmosphere. So what that means is that over here on the western side of the Pacific, over towards Asia and Australia and stuff like that, we've got very warm conditions, and so those warm conditions, okay, lead to rising air. We get our normal convective loop here, much like we would in one of our Hadley loops or something like that. So the warm air goes up, it can go around, and then it's going to come back down over here. So cold upwelling, or cold water and cold upwelling over here, warm water over here, warm air rises over here. What happens in an El Nino year, or El Nino conditions, is that the upwelling actually stops. Okay, and this happens sometimes about every 5 to 7 years, kind of in a cycle. And when that happens, the cold upwelling stops, or at least it's lessened over here, say on the coast of South America. And so what happens is that the warm water starts to go across the equator. And what that means is that instead of it upwelling, or instead of the air above it just heating up right in the western area and then coming back down, is that it's basically heating up over almost all of the Pacific. And that's going to lead to some really weird, wacky weather conditions. We're going to watch a little video on this and talk about this a lot in class, but that El Nino is going to affect and cause some sort of, not really climactic changes, but some weather changes in a given year due to that El Nino condition. And the last thing that I want to talk about, and this, you'll note that this really isn't one of the 5 things, because this isn't really a global pattern, but this is definitely something that affects climate on a day-to-day basis and is going to sort of feed into our biomes. And this is the idea of rain shadows. Rain shadow sounds like a really weird term, but so essentially what's happening here is, like, take the west coast of the United States, particularly up in that area of like Washington and Oregon. So we got a mountain range here. The prevailing winds say that the wind is going to blow in from the west, okay, westerlies. And so the wind's going to blow in from the west off the Pacific Ocean. It's going to come, and what happens is as the wind comes in, it's warm, moist air. It's over the ocean, okay? So it's warm, moist air is moving in, and what happens is as it hits the mountain range here, the Cascades in the case of Washington, it's going to rise up. So as that air rises, okay, because it kind of has to move over the mountains, over the landmass, it's going to rise up. As that air rises up, then the water vapor in it is going to condense, and we're going to get a lot of precipitation. So this is why an area like, say, Seattle, this is why an area like, say, Seattle has like an enormous amount of rainfall, ridiculous amount of rainfall. And it also leads to what we call temperate rainforest, because they're getting a lot of rain there. It's not a tropical rainforest, but they're still getting a lot of rain there. Now, what's interesting is on the other side of the mountain, okay, so all this air has gone up here and it's condensed and precipitated out. The air that actually makes it over the mountain doesn't really have much moisture left. And so on this side of the mountain, there's hardly anything. In fact, the eastern part of Washington is almost like not quite a desert, but it's a really dry, arid sort of area because of this, because most of the rain has been dropped off on the western part over where Seattle is. And then as you go towards the eastern part of Washington, very dry, not much left. These two areas actually have special names for them. So on this side of the rain shadow, we call this the windward side. Okay. And on the other side, this is called the leeward side, where it's really dry. So wet side on the windward side and dry on the leeward side. All right, that's the basics of weather, or at least enough to get us so that we really understand the biomes that are really sort of the heart of this chapter that we're going to talk about next.